Okay, this video is the second half of the 3.1 talking about derivatives. So we looked at the definition of a derivative being the slope of a line that goes through a curve, and we look at the 2 points approaching the same point, meaning they get closer and closer together. So if I want to know the equation for the tangent line then, if I think of a graph, let's just say it looks something like this, and I pick a point on the graph with the tangent line. If I want an equation for this line, I need a point and a slope. So we'll say f of a is our y value, a is our x value. The slope of that is simply going to be the derivative at that point. So we, using point slope, would be y minus f of a equals the derivative at that point times x minus a. So then I can use, the purpose for these lines is a lot of times I can use that line to approximate function values that are really close to the a value. So going on with that, we can then talk about differentiability of a function based on whether or not there is a derivative at a point. So we found how to use the power rule and definition of derivative. The function is differentiable on some interval if it's differentiable at every point. So if you think back to when we were doing the local linearity, when I looked at y equals x squared, if I zoomed in, it seemed to become a line, versus the absolute value, which looked something like this. If I focused in on this point here, the vertex, the slopes were different from both sides, so it never became a line. It always looked like a V. So what we can say then is differentiability implies continuity. But not vice versa. So this function, y equals absolute value of x, is continuous at the vertex, but it's not differentiable because the slope coming in from the left is negative and the slope coming in from the right is positive. So how does that look algebraically then? We say that that means the slope from the right, the slope from the left must be the same. If they're not the same, then it's not differentiable at that point. So for piecewise functions, we first need to look, is it continuous? Yes or no. Are the left and right derivatives the same? If they are, then we have a function that's differentiable. So here's a piecewise function. The first thing I need to know, is it continuous at x equals negative 1? So I'm going to check the limit as x approaches negative 1 from the right. I'm going to check the limit as x approaches negative 1 from the left. And I need to check the function evaluated at negative 1. Evaluated at negative 1, I get 3. And from the right, I get 3. And from the left, I get negative 2. So it's not continuous. At x equals negative 1. So that, okay, sorry about that. Anyway, so since it's not continuous, then it's not differentiable either. Okay, so now, if I have absolute value, if I get derivatives to be the same, that suggests that it's continuous. So I'm just going to check and see if it's continuous, or excuse me, if it's differentiable. Do I get derivatives? Okay, so let's check continuity. Is the function continuous? So as I approach 2 from the right, I get 0, just plugging in 2. If I plug in 2 from the left, I get 0 again, and f of 2 is equal to 0. So it is continuous. So now let's look at the derivative. Is it differentiable? So I now need to look at the slope of, or the derivatives here. So the slope from the left, the slope from the right. So slope is going to be f of x minus f of 2, whoops, that's a minus, over x minus 2. That's our y2 minus y1 over x2 minus x1. So I get f of x is absolute value of x minus 2, minus f of 2 is 0, over x minus 2. So technically I get, this is going to be 1 or negative 1. If I plug in 2 but slightly smaller, I get out negative 1. If I plug in 2 from the right to the same equation, if I plug in something a little bigger, I get positive 1. They're not equal, so it's not differentiable. What we're looking at is the vertex. So that's telling you the slope coming in from the left is negative 1, the slope coming in from the right is positive 1, so the local linearity means this does not become a straight line. It's not differentiable. Let's look at one more. F of x is equal to x to the 1/3. So first let's do at x equals 0. Is it continuous? So I'm going to check the limit as x approaches 0. Now, since the way this function is from the left and the right, I'm technically using just the same function. And if I plug in 0, I get 0, and that is equal to f of 0. So it is continuous. Now, is it differentiable? So we need to find the slope on either side. That's going to be f of x minus f of 0 over x minus 0. So that's x to the 1/3 over x. So that's x to the negative 2/3, which is 1 over x to the 2/3. So I get the limit as x approaches 0 from the right of 1 over x to the 2/3. If I plug in 0, it does not exist. So it is not, if I could spell, differentiable at x equals 0, because that function's not even, the derivative, the slope isn't even defined. And you're going to find if I did the same thing with this one, I'm going to get the same type of answer. You can choose other